Can we want periodic table trends too?
What?
Hold on.
Yep.
Alright, hold on, let me read this.
I didn't want to.
I thought we wanted to talk about the lab for a minute.
We kind of figured it out. We're just gonna kind of do it, and if it's wrong, it's
Oh,
wrong.
wow.
I mean, if you want to tell us if the graph is wrong, then we can.
I didn't do it yet, so I don't know.
Well, cause we
Neither
went
did I.
over it and
What
that's
else are you
exactly
gonna
what
talk
we
to us
got.
about? Like, it's
Whatever
just
questions you guys had.
You just take the ln of the numbers, right?
That's it.
Okay.
Yeah.
Then
Like-
we
Oh,
can-
well, natural log of the absorbance.
Yeah,
Yeah.
that's what we did.
That's what we did.
And then
One over the.
Versus the time, whatever the time is
Yeah.
at those points.
And then one over the
One over the
orbits.
absorbance, yep.
Okay, so yeah.
Okay, alright, what do you wanna do here?
periodic table
I need
trends.
the view sheet.
Shoot.
Boss, you want?
Do you
Periodic
want
table, you wanna go over periodic table trends? That's what you wanna go over?
Stoichiometry.
Stoichiometry.
Yes.
And
Stoichiometry.
solution.
I don't even remember which one it is. Yeah, it's the solution one.
What's the empirical formula? Is just
What's calorimetry?
What is what?
calorimetry?
What is that?
Heat of reaction.
I think I took that off, cause we haven't learned that yet. Actually, no, we have done Q equals MC delta T. We have talked about that. Yeah, and then the heat of reaction, that's exothermic, endothermic, yeah. Alright, so give me one thing, right now, because time goes fast.
Stoichiometry.
Oh, shoot.
Solution stoichiometry. Alright, so that was the questions involving, if you have a solution, it's kind of like gravimetric analysis. Why did you ask me about that? Did I put that word on there? No, I didn't. Chi-Chi came in and said gravimetric analysis.
Yeah, I just said it, but it's not on here,
Right.
so I don't have to.
Give me a second. Alright, so. Alright, if we have two solutions and we mix them, one, can you figure out the amount of product that's supposed to be produced? And two,
Like, can you go over the math of everything?
yeah, I'm gonna give you a
Okay.
problem. I'm just gonna do one from our notes because there's no way you're gonna have it memorized. Alright, so let's do this one. Alright, so we have sodium sulfate solution mixed with lead nitrate. So I want you, one, write out the reaction. And then two, I will give you the concentrations and you're gonna tell me the mass of the product produced. Okay? So you have sodium sulfate mixed with lead 2 nitrate. Sorry, I forgot that too. Lead 2 nitrate. So sodium sulfate mixed with lead 2 nitrate.
Sulfate is SO.
Sulfate's SO4, nitrate's NO3. And you have
So, wait, hmm?
NaSO4 plus PbNO3.
Na2SO4 plus PbNO3 2. Na2SO4 plus, I guess for the sake of time, just Na2SO4 plus PbNO3 2. Those are solutions. So you mix them, they react. So go ahead, write the reaction out. I'll give you some numbers here. And you're going to calculate the mass of the product. So we had 1.25 liters of a 0.0500 molar what is it doing? And that's mixed with 2 liters of 0.0250 moles per liter. So this is a pretty straightforward problem. You write the reaction out. Now the stoichiometry dictate, this is actually, we can review a lot of stuff at once with this. So you write the reaction out, it's double replacement. But the net ionic is all that matters. And then you have to figure out which one's limiting. That's the one that dictates the amount of product. And then you convert to grams. So we're kind of doing limiting, we're doing solution stoichiometry, reactions. There's a lot of
How
stuff.
do you know, like, I don't know how to write the reaction out.
You just write the.
So you just write these two,
Bounce it.
and then hopefully you can recognize it's a double replacement. And the reason you know that is because there's two compounds.
Yeah.
So when you have two compounds or two solutions, it's always double replacement. So your PB and your Na kind of switch who they're reacting with. Na is now with NO3, and PB is with SO4. And then you gotta balance it, so you need two of these. And I think that's it. Oh, forgot my two. Yeah, I think you just need two. So in this case, it's actually even more straightforward because there isn't a subscript or a coefficient in front of these.
When you like switch it over, the NO3 doesn't have the 2 anymore.
No, because it only has a 2 because PB is plus 2 and NO3 is minus 1. You need two of these to balance that out to 0. Over here, Na plus 1, NO3 minus 1. So the net ionic doesn't involve the Na or the NO3. Those are irrelevant. So your net ionic is Pb plus 2, SO4 minus 2 yields Pb SO4 solid. That's solubility rules that factors into stoichiometry problems. So this isn't a great example of confusing stoichiometry because it's all 1 to 1 to 1, but it's still a good example, like good practice problem. Because you need to take the data I gave you, information I gave you, find moles of both of these. Now again, because it's 1 to 1, it makes it easier. So I'll explain how it's different after we go over this problem. But find moles of this, find moles of this. That tells you your moles of these two ions. Then you can figure out how many moles of this you produce. Again, it's all 1 to 1 to 1. And then once you get moles of this, use the molar mass, convert to grams, and that's the answer. But you need to figure out which one's limiting. Is it the lead nitrate or the sodium
Oh,
sulfate?
this is this now.
So, first convert these to moles. Then, figure out which one's limiting. And if you want to stop there, and we'll go over that part. And then we'll go over it. What did Nicole say when she came in?
She ran out, she's like, oh, Miss Riss,
Oh, right.
or something,
Yeah,
somebody.
she had to go. Okay.
Yeah, she was gonna ask me.
Yeah, that's fine. We're doing it. Skylar, I still have your name up there because we do need to do that homework stuff.
I mean, you said you were gonna make like a sheet.
Yeah, but then I told you in forensics I can't really do that.
Oh, you did?
Yeah, maybe
You
I.
didn't tell me that.
So,
How do you know how to get the net ionic?
net ionic only includes ions that actually react. The Na plus and NO3 are called spectator, and the way you know that is because sodium nitrate is aqueous. So basically, your NO3 minus, your Na plus are floating around in this solution, this reaction not doing anything. So those ions mean nothing, so they're not in the net. The net ionic only contains ions that actually produce a precipitate.
So, anything that's not aqueous?
Yeah.
Right. It's aqueous here, initially, because lead nitrate is soluble, sodium sulfate is soluble, but when these two ions get together, they're not. So that's what net ionic is. So you need the solubility rules for that.
The solubility rules for what?
To figure this out, you need to know this is a solid.
Oh.
Otherwise, you can't figure that out. You just guess. Am I being clear?
Yeah.
All right, how many moles of lead nitrate do we have?
10625.
0.0625?
Yeah.
Okay, good. And how many moles of this?
0.05.
0.0.
0.05. All right, So this tells me at 0.05 moles of SO4 minus 2 and at 0.0625 moles of PB plus 2. And this is my whole weird thing. If you have a mole of marker, you have a mole of cap. And what that means is PbNO3 2, if we use magnets here to help us maybe understand. So if PB is yellow and the NO3 is green, if I have 0.0625 of these, I have 0.0625 of just PB as well, because there's only one PB in one of those molecules. If I have 10 moles of the PbNO3 I have 10 moles of PB. I would have to double this number for NO3. Same thing here. I had 0.05 moles of this, so I have 0.05 moles of SO4, but I actually have twice that for Na. I have 0.1 because there's 2 Na for every 1 SO4. That's a really important concept for a lot of questions. And if you know the moles of a compound or a molecule, you know the moles of part of that molecule, that's 1 to 1, and if there's 2 or 3 or 4 atoms, then you have to multiply that number by whatever that is. So again, because there's 1 PB, that number is the moles of PB. Same thing here. Does that make sense? Hope so. Because that's important. If this was 2 PB, then you would have to double that, then use that down here to find the product. Okay, so this we have 0.0625 moles of these, and then 0.05 moles of this. Now again, this is all 1 to 1 to 1, so this is a lot easier than a typical AP limiting problem. And that would be if there's a 2 or a 3 somewhere. But anyways, who's limiting? Which one is going to produce the smallest amount of product? That's what limiting does.
SO4.
Why?
It's less moles.
Right. So if these two react as a 1-to-1 ratio, this is going to run out first when they come together. You're going to have excess of this. Does that make sense? Okay. So this is exactly how many moles of PbSO4 you're going to make. You don't need to do a calculation because it's 1 to 1. So that's how many moles of lead 2 sulfate, sorry. Now just convert to grams. And that's your answer. And then we'll do another solution problem except working backwards. Because it's the same thread here, same concept. Questions?
I tried 0.5.
Oh, I'm sorry. I forgot my 0. Sorry. 0.05. Yeah, those numbers are the same. After we do another solution problem, I do want to talk about trends. I think that's a good thing to talk about because the trends help you answer a plethora of AP questions. Alright, so you should be done by now, I hope. Anybody? Yeah, you look like you're in pain.
No, you're just, well, it's just over one from.
I got 151.5.
You're off
I
by
got 15.05.
Oh.
Yeah, it's because I wrote,
Yeah,
I screwed
she
you up.
copied you.
Sorry. So 15.2.
Yeah. 15.
Yes.
15.
Sure. I rounded 3
15.15.
sixteenths. 15.15, 15.2. Good. Alright, so that's kind of like going one direction where they give you the reactants and then you figure out products. I'm going to give you another question where it's the same type scenario, except I'm going to give you the mass of products. You have to tell me how much, what's the original mass that was dissolved, right? So you work backwards, but it's the same concept. You're just starting with this and then going this way. So, let's do one of those here and then we'll move on. Alright, so let's say we have, where is it? Okay, actually, this is a little bit harder, but that's okay. It's the same concept. All right, so let's say you have an unknown compound with the bromide ion. It's treated with, I'm not going to make you figure out the identity of that. That could be a good question, but I don't trust myself to make up the numbers very quickly here and have it work out. So, it's treated with X. So this is how they're going to word the question. You have a compound with the bromide ion in it. It's treated with excess. Sorry, this is the solution. It's treated with excess silver nitrate. What's the point of that? What's excess? Why are they telling you that?
So you know that's limiting.
This is limiting. So when this is treated with excess, you get XNO3, which no one cares about, and then you get your AGBR, which is a solid. So again, you need to, well, they would tell you that. They would say, okay, the product, they may give you the formula, AGBR. In fact, they have to. They have to. They say, okay, the product, silver bromide, is produced, filtered, dried, and massed. And you get a mass of 0.464 grams. Calculate the percentage of BR, in the original compound. Now, the other information I have to give you is the mass of this original compound. So the mass of this compound was 0.250 grams. So they give you the mass of the original compound. You don't know what the formula is, though. So you do know you took 0.25 grams, dissolved in water, added excess silver nitrate. That's your precipitate. They filter it, dried it, masked it. They want to know what's the percent BR in that. The fact that this is excess is the key here. That's the important part. So Chichi, when you said gravimetric analysis, that's what this is.
Yeah,
Because
yes.
you would use gravimetric analysis is a fancy way for, say, filtration. So you let this filter out, then you dry it, weigh it, and then with that information, you can figure out other things.
Yeah, that's what I just realized, that's what I was doing, this was.
So, no, it's still, it's good to be able to do both problems. We're reviewing more than just like one thing at a time here, so. All right, does anybody have an answer?
80%.
Yeah, about 80%, about 79%, 78.8% is what I got. So the way I did it, the way I would do it, turn this to moles. Why? Because if all of the BR is here, and how do I know that? Because you saturate this solution with more Ag plus than it can handle. So literally all the Br minus will precipitate. So all the Br there is the same as all the Br here. So if we find moles of AgBr, and that is, I did it a different way in my notes, but I don't like the way I did it. Who did that? Who had moles of anybody?
0.0025.
0.0025 moles of Br minus, right? So 0.0025 moles of AgBr is 0.0025 moles of Br minus. We know the mass of this compound. It doesn't matter what that is. We know the mass because it told us. So now what do we do? What's the next step?
Find how many grams of BR we have.
Right, so take 0.0025, use 79.9 or 80 grams per mole of Br. Let's convert this to grams of Br. And what'd you get for that, Tristan?
We have 0.2.
Grams of Br would be 0.2 grams, right? Everybody else with in there? Whoever, didn't someone over here get that number? 0.2. Okay. So then what'd you do?
Divided like 0.2 by 0.25.
Right,
5%.
so now you got your XBr, right? We know this part of the compound is 0.2, but we know the whole thing is 0.25. So percent Br would be 0.2 divided by 0.25, and that equals about 79%. I got 78.8, and I didn't have 0.2, I had 0.197. It's
Yeah, that's.
3 thousandths of a difference, right? Yeah, whatever. So 0.2 is fine. So again, with these problems, if they give you the precipitate's mass, it's because one of the reactants they're going to tell you is excess. So all of the other, whatever the ion is, all of it has to be precipitated. That's how you can work backwards. So if you know the moles and grams there, it's the same as it is here. And that's how we would do percent, part over whole times 100. Now let me ask you this question. If this was given to you on a AP test or midterm, let's say, and then, you know, let's say part A was this, what's the percentage of BR? Part B might be, if this is correctly balanced, in other words, there's only one X here, one X here, there's no coefficient. So this is the balanced equation. What is the identity of X? Would anybody have an idea of how to do that? I don't think I'd put one on the midterm, so I'm not going to spend a lot of time on
Don't you just
that.
use the like percentage
Yeah,
and find
you
the
could
grams of X and then use like whole amount?
Yeah, you could use the percent. So what percent is X? Roughly 21%. So if you did 21% of 0.250, you could get the mass, or actually you could just subtract, right?
Yeah.
It's 0.05, right? So you have 0.05 grams of that. How does that help you get the? You're right. You're on the right track here.
Well, then you have the moles, the 0.025 moles.
Oh, you multiply by that moles, because if you have 0.0.
Well, if this is if this is 1-to-1, you have 0.0025 moles of Br. You should have the same moles here.
Yeah.
So then, how would you get molar mass?
That's how many.
What's the
that's how
unit?
many moles
What's the
per
unit
gram.
on molar mass? Grams per mole. So what if we did 0.05 grams, right? Divided by 0.0025 moles. Let's see what you get. See if it works. Yeah. So this problem wasn't intended for that, but what element would be close to that? I did it and I said 20. Yeah, but it can't be neon. It's got to be metal. Yeah, Na. Na would be closest. I'm just explaining that to you. This problem wasn't designed for that. They would have to change this number so that this was closer to Na. But again, I'm just trying to help you with future questions here. All right, trends. So are there any trends in specific trends that you don't know? When I say trend, you even know what I'm talking about? Okay, like what? How about radius? Good, let's talk about radius. What's the trend on the periodic
Oh,
table?
it, left to right increases.
What increases?
No.
The atoms get smaller.
Wait, yeah.
Here's the
Down.
yes, Coulombic force increases. Here's what you guys need to know, and this will help you immensely in tests and midterms. This corner and this corner are opposites for all trends. That helps because if you can remember one of them, then all the rest fall into place. So down here, they have the largest radii, smallest radii. Weakest Coulombic force or effective nuclear charge, strongest Coulombic force or effective nuclear charge. High electronegativity, low electronegativity. High electron affinity, low electron affinity. High ionization energy, low ionization energy. There are exceptions, and that's where the AP test will get you. And it's like they're gonna say, okay, you know, moving left to right in period 3, ionization energy increases. But explain why phosphorus has a higher ionization energy than sulfur. So then you have to write out the electron configuration, look at the arrows in the boxes, and say, okay, what's going on here? Why would sulfur lose its electron easier than phosphorus? We don't have time to go over every single little thing, obviously, in these review classes, but I'm just trying to review. That's the concept. So it's the exceptions. They're not going to say, what is the trend in ionization left to right in period 2. That's reading stuff. They're not going to do that, maybe. But it's really important you remember what I just went over. I'll say it again. The bottom corner here, that is opposite of the top right corner. Biggest radius, smallest radius. Low electronegativity, low electron affinity, low ionization, and then high for all of those. Why going down a group does radius get bigger, but going left to right does radius get smaller? That's
Wait,
the
sorry,
question
what?
I want you to answer.
Sorry.
It's more electron levels.
More shells, which, but
More
more shielding, good, what else?
More electron.
Propulsion.
No, that's going.
Because there's more shells, there's weaker
Coulombic
Coulombic force between the protons and those electrons. But when you move left, it's the same number of shells with more electrons in them, but the proton number increases, so there's a stronger Coulombic force. So any short answer question involving those trends, you can't just say more protons, more electrons, stronger pull. That's kind of like Regents terminology. You have to use Coulombic force, electrostatic. You got to use those terms. This is out of here. Okay. See you, Liz.
Good luck.
What's going on?
She's doing like a video conference.
Good luck.
I'm so nervous.
You'll be fine. Just be yourself.
It's an hour and a half.
Oh,
What's this for?
It's for like something.
FFA or
I don't think
something?
she's
Like
doing
a
next
dumb
year.
bunch. She's the
Oh,
only.
because she wants to do the
No, it's
internship.
not that.
Oh, it's not.
It's like she's the only one there
I was.
too. She's gonna be talking to like a ton of different people.
Wow.
Yeah.
All right. What else? We only got a little bit of time here today. What else on that review sheet? We kind of just went over some atomic structure theory, periodic table trend stuff. Oh, PES is on there.
What is all that?
That's part of atomic theory. That's stuff you guys didn't have a problem with. That's the peaks where if it's
Oh,
high,
that's
there's
easy.
more electrons.
I thought it was over.
Yeah, so that, you know, the 1s2, 2s2,
oh,
binding energy. The closer to the nucleus, the higher the binding energy bit. What else?
what would be there for molecular and empirical terms?
So, so the typical ones are those problems where you burn something in oxygen and you have to get the empirical formula of that something.
Can we do that?
You want to do one of those? All right, we can do one of those, and that's all I'm gonna have time for. But it's all right. We'll talk about some good stuff here. So if you guys can maybe come up with some specific things or at least topics, give them to me tomorrow or Monday in class, so I can have a little bit more ready for Monday. Just be a little more efficient with the time. All right, here we go. Here we go. You have 23.2 gram sample of an organic compound containing CHNO. So 23.2 gram sample. It contains CHNO. It's burned in excess oxygen. Again, the reason they say that is because all of the CHNO in that compound are now found in the products. All right,
What was the first number?
23.2. So you got 23.2 of CHO. We don't know these subscripts. Excess oxygen, you get, this is combustion, so you always get these two. You get 21.6 grams of water, and you get 52.8 grams of CO2. Calculate the empirical formula of that.
See, math. I hate everything math related.
Well, this class has a lot.
Yeah, but no wonder
And we're just
not
getting
really.
ramped up. Empirical, or I mean, equilibrium, there's a lot of math. Acid-base, a ton of
What
math.
if like we fail the midterm?
Yeah. What if like all of us do really
You're
bad?
not gonna fail it.
Okay, then what if we all get like 70s?
Yeah, what if we all get like really bad?
That's
Not
pretty
failing.
good, actually.
That's good. So
If
your
the class
plan,
averages in the 70s, that'd be okay with that.
how much is this
I
weighted
wouldn't, I would
towards
cry.
your grade?
It's just, it's gonna count what it, it's gonna sound stupid, like what
Here's
it
what it
counts.
is.
So I'm not like triple weighting this thing or anything.
Okay.
It's just
So
like
it's
a
like
test.
one
So just a
It's like one test.
Okay.
Let's
So
kill
we're
you.
spending this whole time on one test.
Yeah. It's a lot of points. I mean,
Oh,
it's
yeah,
a big test.
No, I know, I don't want to.
And the reason I'm doing it is because I want you to experience taking an AP test before you take it.
It's an AP test, right?
Every single question's from an AP test.
And you're timing us and
Mhm.
everything.
Ooh.
So you're gonna be
Mhm.
standing there like being like, stop, start.
Yeah, I mean, I
And
won't
are we
say it
doing like the
that.
no calculator?
What?
Are we doing like the no calculator for?
Mhm.
Oh,
There's gonna be like 60 multiple choice, I forget what it is, 50 multiple choice or 60, and no calculator.
Oh my.
Are we taking it Wednesday or is it Thursday?
Wednesday after school, Thursday in class and after school, and then Friday in class.
Okay, Wednesday. I'm gonna leave class like 2 minutes early because I have to go watch Max do a presentation.
Sure. Alright, let's do this quick here, because I gotta skedaddle. Hey,
No.
that's alright, it's fine, it's just, I'm recording since it's review for our midterm and some aren't here, so.
Gotcha. I wanted to know if when I get a chance, I talk to that Professor Goshko Landis.
Oh, yeah.
Want me to kind of set up something so we can chat with him
Sure.
at some point, even if it doesn't work out on that day or something?
Right, yeah, I mean, I'm probably gonna back out of that, just because it's so close to the AP test, but maybe not. Maybe at that point, I can just give them stuff to do and I don't need to be
It's already
here.
enough.
Okay.
So,
All right.
so, yeah, definitely,
No, he would be able to help you immensely.
yeah,
So
okay,
he's a good guy.
yeah, that's, I hear nothing but good things, so. Okay,
Yeah, that's right.
Yeah, I have no idea what.
It's a good job.
find moles of CO2 and moles of H2O. How does that help us?
Those are the moles of C, moles of H. moles of
Right,
O.
all the C and all the H here are found right here and right here. So if you find moles of C and moles of H, hydrogen, that's the exact same as here, then you just gotta find oxygen. So we'll finish this.
You just finished it on there and then just end it.
Yeah, this is it, what do you mean? I don't know what that means. What do you mean?
Yeah, this is all right.
So you're leaving?
Yeah, I gotta get the glass.
Alright, I'll just do it right now. Okay, so I'm confident you guys can all convert these to moles. Who found moles of CO2?
1.2.
1.2 moles of CO2?
Yeah.
So that's 1.2 moles of C. Because there's one C in CO2. How many moles of water?
1.2.
1.2 moles of water. So you have to double that, 2.4 moles of H. Because if you have 1 mole of water, you really have 2 moles of H, because there's 2 of them in it. So now that means I have 1.2 moles of C and 2.4 moles of H. Convert them to grams. That's 2.4 grams of H, because the mass of hydrogen is 1, right? So that's the same. How many grams of carbon are in 1.2 moles?
14.4.
What is it?
14.4.
14.4 grams of carbon. Okay. So now what you do is you take 23.2 minus 14.4 for the C, minus 2.4 for the H. That'll give you the grams of oxygen. 6.4?
Yeah.
6.4 grams of O. Now use the molar mass of O, 16 grams, and get moles of O. And I'll tell you why I need to do that in a second. So you gotta convert this to moles of O. And that is, anybody? 0.4. So now to get empirical formula, you take the moles of O, moles of C, moles of H, divide by the lowest number, and then that will give you your atom ratios. So if you do 1.2, 2.4, and 0.4, you divide by 0.4, you get, what is that, 3, 6, and 0?
Yeah.
So it's C3H6O. That is your empirical formula. Or not 0, 1. Sorry, that's impossible. 1. So I went quick, but that's how you do all of these types of problems. So it's a good example. All right.
I knew about that.
Yeah. With the limited time we had, that was pretty good.